In our last video, we were talking about the dynamics of the moving system. We have mentioned about the importance of damping, the damping torque. It should not be very small because then the system will oscillate. It will take long time before we can take reading. It should not be very high, then the system will be over damped, which means it will not oscillate, but it will take time to reach its final position. We have found the condition for critical damping, that is the condition where the damping is just perfect. The system will not oscillate, it will not take more than the minimum required time to reach its final position, that is the critical damping condition. And we have also mentioned in particular where we use eddy current damping, how should we choose the value of the resistance of say the former if we are considering the eddy current damping due to the eddy current in the former or the aluminum frame on which the conductors are wound. So, we have discussed how much should be the value of that resistance, former resistance, to get optimal best value of the damping. In this video, we will talk about an interesting application of this analysis of say the dynamics of the moving system. So, we will talk about ballistic galvanometer. What is a galvanometer? A galvanometer is nothing but a PMMC instrument, permanent magnet moving coil instrument. A galvanometer is another name of PMMC instrument. And by the word ballistic, okay, ballistic means it is a galvanometer which has very little or almost no damping, no friction. Okay, it is almost no I mean it's a frictionless, dampingless galvanometer. So, the constant damping constant is ideally 0 for this galvanometer. We will talk about how we can use this fact that the damping is 0 to measure charge flown in a short duration during a impulsive current using ballistic galvanometer. Okay. So, we will measure. So, today we will measure charge flown during a impulse current. Okay. So, what do we mean by an impulse current? Suppose if I draw say time versus current in any any conductor in any branch of a circuit, if I have any arbitrary pattern of the current, this is time, this is current, then call it I, then I t dt, this integration between 2 points t1 and t2 is nothing but the charge that flown from one point of the circuit to the other between the time interval or in time interval T1, T2. Okay. So, if this is T1, this is T2, if we perform an integration, that is the area under this curve, this is nothing but the charge flown within that time. Now, an impulse current is a current which exists for a very short duration, maybe it is like this. So, it is 0 here it is 0 here, but it is non-zero only for this small time interval. Okay, and this time interval t1 t2, so the gap between t1 and t2 is almost 0, so this tends to 0. Okay, this is what happens for an impulse current. But if we perform the integration within this time, okay, the integration of this current it, this should be a finite number. Okay, that means the amount of charge that flows within this time, that is not 0. Although the current exists for a very short duration, but a finite amount of a non-zero amount of charge is transferred within this time, which also actually means that the height of this should be very high. I mean, the maximum, the amplitude of this current should tend to infinity. Okay, that is what an impulse current is. The current is of very high value, it's almost infinity theoretically, but it exists for a very short duration. Therefore, a high value, very large height multiplied by a very small width, that comes out to be a finite number. It is neither 0 nor infinity. So, the charge flown within this time, that is the area under the curve, is a finite number, and particularly if this area is equal to 1, we call that an unit impulse. You may know that. Okay. Now, the goal of this video is to measure this charge which has flown during an impulsive current in a circuit using a galvanometer, which you call the ballistic galvanometer. Okay. So, okay, in a ballistic galvanometer, the damping constant is 0 ideally. Okay, so there is no damping force, no damping torque. Now, say impulse current flows through the coil of the instrument for a very short duration. Okay, so impulse current flows. Okay, now if we call this current as I, okay, then we know that I multiplied by G, G is what? The galvanometer constant, which is BAN, that means force per torque per unit current. This is equal to the torque. Okay, and therefore, this should be equal to the moment of inertia multiplied by the angular acceleration. Okay, so this is the or we can say that this is the rate of change of the angular momentum. Okay, so this is ddt of the angular momentum, which is given by j d theta dt. This is nothing but ddt of the angular momentum. rate of change of momentum is force, and rate of change of angular momentum is torque. Okay. Now we know that this I, which is a function of t, is impulsive, so it flows for a very short duration, say dt. Therefore, if we multiply this with the time dt, okay, then we will have rate of change of angular momentum. So let me write it in language. Rate of change of angular momentum multiplied by dt. So this will be the total change of angular momentum in dt time. Okay. And the left side will be g times q. This I dt is equal to q. This is the charge flown in dt time. Okay. And this is what we want to find out. We want to find out the value of q. Q is unknown, and we want to find q. Okay. So we know gq is equal to total change of angular momentum in dt time. Now assume the coil was in rest before the impulse current. Okay. So therefore, the initial angular momentum was equal to 0, and the total change of angular momentum, we have found that this is equal to gq. Okay. So the total change of angular momentum is gq. Now total change of angular momentum is nothing but the angular momentum after the impulse current minus the initial angular momentum, which was 0. Therefore, we can write this is same as the angular momentum after impulse current. So gq is equal to angular momentum after impulse current, and then this should be equal to j times omega, where omega is equal to the angular velocity after immediately after the impulse current. So immediately after. And j is of course moment of inertia. So therefore, we can find the velocity omega immediately after this current has flown as gq by j. Okay. So if this is the angular velocity, then how much kinetic energy do we have immediately after this charge has flown, this current has flown? So that will be given by, so the kinetic energy immediately after the current, impulse current, this will be equal to, we know it's like half mv square for linear motion, and in this case it will be half j omega square for angular motion. So, this is the kinetic energy immediately after the charge has flown. Now, what will happen? The charge has stopped, the current has stopped, but this current has set the coil into motion. The current has stopped, but within that short time the coil has already started to move, the coil has already gained some velocity, gained some kinetic energy. And then when the current has stopped, due to inertia, the coil will continue to move. And as the coil moves, the angle theta increases, therefore, the spring tries to stop it. So, spring now wants to stop this coil, but due to inertia, the coil will go up to some distance. How far will it go? It depends on the initial energy it has immediately after the current has stopped, and that energy, as we have written right now, is half j omega square. So we have to find out with this energy how much can this coil move, and let us assume the coil can move up to an angle say theta f for final. So, assume the coil can move up to an angle theta f, means final angle, okay, when the coil will stop. So, assume the coil can move up to an angle theta f with this kinetic energy. Okay. So, as the coil is moving, as the theta is increasing, this kinetic energy will be used, and that will get converted into the potential energy of the spring, and the potential of energy of the spring is given as half k theta square. So, at its final position, when the pointer stops, the kinetic energy will become 0, potential energy will become same as the initial kinetic energy, because the entire kinetic energy will be converted into potential energy. So, the final potential energy in spring will be equal to half k is spring constant, multiplied by the angle theta f square, and this should be equal to the half j omega square, which is the initial kinetic energy. This is conservation of energy. Okay. So, therefore, we can write half k theta f square is equal to half j omega square, and previously we have seen that the value of omega, that is the angular velocity immediately after the current, is given by gq by j. So, let us put it. So, let us put the value. Okay. So, now we can cancel this half from both sides, and so we can write k theta f square is equal to j, here we write gq by j whole square. Now, we will take a square root. So, we will write this as k by j square root of this multiplied by theta f, this will be equal to GQ by J. Okay, verify this yourselves. I may do some mistake in while manipulating this. So, verify this once again. So, K divided by J, root over of that, theta f, this side is GQ by J. Okay, it seems correct. If so, then we can write Q is equal to root Kj multiplied by J divided by G and theta f. Okay, K by J, root over that, then J divided by G and theta f. Okay, so therefore, and you see all these terms are so you can write this as root over Kj divided by G multiplied by theta f. Q is the unknown that we want to find out. All these terms K, J and G, these are all constants. So, these are all constants for a meter. Okay, and theta f is the angle, is the maximum angle where the pointer or the coil moves. Okay, so we can measure this, we can observe this. So, this is measured or observed. And then if we know these constants, if we measure theta f, we can find the value of Q. So, that was our target. So, we have achieved it. How to find the value of Q? So, how to do it? Very quickly, let us summarize how will we do it experimentally. We will let the impulse current flow through the coil and then the pointer will start to move and it will start to oscillate. Okay. So, if the pointer is here initially at its 0 position, and if then the impulse current flows, it will set the pointer in motion, it will give it some kinetic energy. So, it will start to oscillate, it will go to some extreme position and then it will oscillate. Okay. As the impulse current flows, it will start to oscillate and we have to measure this amplitude of oscillation. That means how much it's going, what is the maximum angle this pointer is reaching. That is the value of theta f, maximum angle that the pointer is reaching. This theta f, if we know, if we observe this amplitude, okay, this is the amplitude theta f, we will put it here in this expression and we can find the value of Q. So, this is how we can find the value of unknown charge using ballistic galvanometer, and this will be important later on when we talk about magnetic measurements. We will see that with this we can with this mechanism we can measure flux density in some core, in some toroid, then this mechanism will be useful. So, right now you just understand how to measure some charge during an impulsive current. We will make it more useful later on in our course. Thank you.